Hi guys, today we're going to be learning about aldehydes and ketones. So first I would like to give you an outline on what we're going to be studying in this chapter. So the first thing that we're going to be learning about is the difference between aldehydes and ketones. So towards the left I've made an aldehyde, and as you can see there's a terminal hydrogen attached to the carbon that is attached to the oxygen. So in all aldehydes there needs to be a terminal hydrogen. Whereas towards the right I made a ketone, and this central carbon over here needs to be attached to two R groups, so in this case there is no terminal hydrogen. So this is the difference between aldehydes and ketones. After this we're going to be going over the physical properties of aldehydes and ketones, and then we're going to be talking about the main thing, which is the reactions. So the reactions can be classified into two types. The first one is reactions that are exhibited by aldehydes only. In this case you have two. So you have the Felling's reagent test and the Tollens reagent test. After this, we have reactions that are common to both aldehydes and ketones. So in this case, you have four main reactions. There's nucleophilic addition, reduction, condensation, and the iodoform test. And after this, we're going to be going over the uses of aldehydes and ketones. Now let's talk about the physical properties of aldehydes and ketones. And we're going to classify this into two types. So we're going to be discussing intermolecular forces and bond angles and shapes. So the intermolecular forces over here are going to be ID, which is instantaneous dipole and induced dipole, and PD. So in this case, what's going to happen over here is, since you have a dipole, because oxygen is more electronegative than carbon, you have PD forces over here, and ID forces exist in all molecules. So in this case, no hydrogen bonding will take place. Why? Because this hydrogen over here is not directly bonded to fluorine, oxygen, or nitrogen. So in this case, no hydrogen bonding will take place. However, hydrogen bonding will not take place between molecules of the aldehyde, but hydrogen bondings can take place between aldehydes and water, as demonstrated over here. So you have the hydrogen bond between a lone pair of an oxygen and a hydrogen. So this is going to be your hydrogen bond that's forming over here. Now, the thing is, this hydrogen bonding is only exhibited by lower aldehydes, because as you go down the aldehyde group, the carbon chain will increase and the molecule will become less polar. So it's going to start to repel water. So in this case, only aldehydes which have less carbon can form hydrogen bonds with water molecules. Now let's discuss the bond angles and shapes. So over here I have an aldehyde. Now I'm going to mark the central atom. In this case, the central atom is a carbon. And around this carbon, you have three regions of electron density, which corresponds to 120 degrees. And the shape is going to be trigonal planar. In this case, you have no lone pairs. Similarly, over here, the central atom that you have is carbon. And this carbon will be surrounded by three regions. So it's going to be 120 degrees and trigonal planar. And since there are no lone pairs, you won't count that at all. Now we're going to be discussing nucleophilic addition. In this case, the reagents are going to be aldehydes or ketones, depending on what type of reaction you want to do, and hydrogen cyanide. And the conditions are going to be NaCN as a catalyst. So now let's discuss this reaction with both aldehydes and ketones. So the first thing that's going to take place is that this oxygen is going to have a partial negative charge and the carbon is going to have a partial positive charge, because oxygen is more electronegative than carbon. The cyanide ion, which is going to be the nucleophile, will be attracted to the partial positive charge of the carbon, and this is going to form the intermediate. This intermediate is going to be very unstable because this oxygen has a negative charge. This oxygen will form a dative bond with the hydrogen of HCN, which is the reagent that we are using, and this is going to result in the formation of a cyanohydrin. A cyanohydrin is a compound in which an OH group and a nitrile group are bonded to the same carbon. So this is the reaction of HCN with aldehydes. And now we're going to be discussing the same reaction with a ketone. In this case, something very similar is going to happen, is that the cyanide ion is going to be attracted to the partial positive charge of the carbon, and it's going to result in the same intermediate. After this, the same oxygen atom is going to form a dative bond with the hydrogen, and it's going to result in the formation of a different cyanohydrin. So this was nucleophilic addition of aldehydes and ketones. Now we're going to be discussing the second type of reaction, which is going to be the reduction of aldehydes and ketones. We can classify this into two types. The first one is reduction using reducing agent, and the second one is catalytic hydrogenation. So the reducing agent that we use for this reaction is going to be sodium borohydride. Now let's look at it separately for aldehydes and ketones. So in this case, you have a 2-carbon aldehyde, and this is going to be reduced to a 2-carbon alcohol. So aldehydes are reduced to primary alcohols. If you want to learn more about primary alcohols, you can check out the video on alcohols. After this, we're going to look at ketones and their reduction. So this is a 3-carbon ketone, and it's going to be reduced to a 3-carbon alcohol. In this case, it's going to be a secondary alcohol, as the central carbon is bonded to 2 other carbons. The next type of reduction is going to be catalytic hydrogenation, and for that you use nickel catalyst at 5 atm, and the process for reduction is going to be the same as the one that I've already drawn towards the left. Now we're going to be discussing condensation, which is the third reaction exhibited by both aldehydes and ketones. For this, the reagent that we're going to be using is called 2,4 dinitrophenylhydrazine. And the condition is that this reaction takes place at RTP. So for this reaction, the reagent is drawn over here. The structure that I'm drawing right now is called hydrazine. And hydrazine is a part of the reagent that I've made in pink over here. So in this case, one of these hydrogens gets removed. So this is the hydrazine part of our reagent. After this, we have the phenyl portion, which is shown by this benzene ring. So when a benzene ring is a substituent, it is known as phenyl. And we have 2 nitro groups over here, which are attached to the 2nd and the 4th carbon, which I will number for you right now. So this is how you get the name of the reagent that we're using, 2,4 dinitrophenylhydrazine. Now let's look at the reaction with aldehydes and ketones. First, let's look at the reaction with aldehydes. So in this case, what I'm highlighting will be removed to form a water molecule, since this is a condensation reaction. So you are going to remove an oxygen from the aldehyde and H2 from 2,4 dinitrophenylhydrazine, and these two are going to combine to give you water as one of your products. So what you're going to get over here is going to be this substance as well as water. And for ketone, a similar reaction will take place. 1 oxygen and 2 hydrogens are going to be removed, the oxygen from the ketone and the 2 hydrogens from the reagent that we are using. And in this case, a double bond is going to form between a carbon and a nitrogen over here and over here to compensate for the bonds that are lost when hydrogen and oxygen break off. So this is a condensation reaction of aldehydes and ketones. The observation for this reaction is that a red precipitate will be formed. Now let's talk about the last reaction that is exhibited by both aldehydes and ketones, which is called the iodoform test. If this test is positive, you will get a pale yellow precipitate. And this test will only be positive if your carbon, which is bonded to the oxygen, the central carbon, is bonded to a methyl group. So in this case, the central carbon is bonded to 2 CH2 groups, and there is no methyl group which is directly bonded to the central carbon. So in this case, your iodoform test will not be positive. In the second example, the essential carbon is bonded to a methyl group over here. So the iodoform test will be positive. Now let's look at the different equations for these reactions. For this, you need iodine dissolved in water and 4 moles of sodium hydroxide. And in this case, this methyl group is going to be used to form iodoform, which is going to give you your yellow color. You're going to get a salt, 2 different salts, and you're also going to get water. And the similar thing will happen to ketones. So you're going to get a salt, iodoform, another salt from which these ions come, and you're also going to get water. So this was the iodoform test.